goes on to Pete. So Monday, just to review a little bit, we talked about mass spectrometry sort of as a general overview, and its coupling to liquid chromatography and chromatographic interfaces. And as introduction, I gave you an overview of different mass spec sources, what types of ionization sources there are, what types of mass analyzers there are, and what their strengths and weaknesses are, specifically from the standpoint of coupling to liquid chromatography and doing quantitation. I probably don't have 50 minutes worth of straight lecture material here today, and I want it to be a little bit more interactive. I'm going to talk, so interrupt me at any time, ask questions if things aren't clear. If you have specific quantitative applications you'd like to talk about, we can talk about those. But basically, what I want to do is I will do a brief review of sort of LCMS and what type of mass analyzer is the best for doing quantitative analysis of low levels of compounds in mixtures. And then using liquid chromatography coupled to a triple quadrupole mass spec as sort of a model box for doing liquid chromatography mass spectrometry quantitation, because it's sort of the instrument of choice in the field. We'll go through a couple of examples of quantitation doing this, using this sort of instrument, how you'd set up the method, how you'd run it, and two different ways to do the quantitation, and the advantages and disadvantages of each. So we'll go over a typical external standard quantitation and then talk about the limitations of that and go into doing quantitation with an internal standard and why we do that, especially in LCMS and why it's important. Key application areas right up front for doing quantitative LCMS. If you gain experience in this, it's a very marketable skill. There's employers everywhere looking for people with LCMS experience, especially people who understand how to do quantitation in complex mixtures. It's an enabling technology in environmental analysis where you're doing pesticide screens, looking at pharmaceuticals or personal care products, perfluorochemicals in the environment, sampling river water and lake water and streams, and looking at the environmental impact of a variety of compounds. GCMS and LCMS are going to be your two enabling technologies in that area. Food and food safety, which is becoming, a real forefront sort of scientific endeavor in industry. Antibiotics, acrylamide, melamine, cyanuric acid, or health beneficial compounds in food. LCMS is going to be a technology that's going to be used very often in that field, primarily because there's just nothing more complex than a food matrix. You've got protein, you've got carbohydrate, you've got all of these different chemical moieties that really interfere with analyses, and having the specificity of mass spec to go in and pull things like this out of those complex mixtures and be able to say, are they there or aren't they, and how much is there, becomes very important. Forensics, counterterrorism, looking at terrorism agents, drugs of abuse, in a variety of matrices is going to rely on both GCMS and LCMS. The pharmaceutical industry, if you go to a place like Pfizer or Eli Lilly, they have warehouse-sized buildings filled with LCMS instrumentation, going 24 hours a day, looking at drug metabolism, pharmacokinetics, and using them for new product development applications as well. And finally, in just general biotechnology, doing metabolite profiling in organisms that are engineered to produce compounds that are typically derived from petroleum products, or any sort of new product development in the biotechnology arena, including protein structural characterization, enzyme structural characterization, and small molecule quantitation. LCMS is going to be there for that. So that gives you sort of an idea of the power of the technique and the utility of it in the real world. We talked on Monday about all of the different mass analyzers that could be used for quantitation, and I hope I got it across to you that really the most powerful mass analyzer to use and most reliable to use in terms of doing accurate quantitation at low levels of complex mixtures is the Quadrupole mass analyzer. In addition to the performance characteristics, which include a wide dynamic range for quantitation, a wide linear dynamic range that's required for forming good calibration curves and getting accurate quantitation, and high duty cycle of a quadrupole mass analyzer, so that if you have high efficiency chromatographic separations with really sharp peaks, being able to take 20 to 40 to 100 scans per second using a quadrupole is going to give you a lot of detection points across a peak. You're going to have a nice peak shape. You're going to be able to measure that area very accurately and do accurate quantitation as a result. So for the examples we're going to talk about today, I'm going to focus on using a dual mass analyzer or a triple quadrupole mass spectrometer at the back end of whatever chromatography system you might be using. In which case we've got our ionization source. Typically 90 to 95% of the Lcms applications you're going to see doing quantitation is going to be electrospray ionization, which we talked about before, where you're taking a liquid flow off of the LC, desorbing those ions into the gas phase, and they're going into the mass analyzer to be separated and detected. You will see things like atmospheric pressure chemical ionization for compounds of higher, more hydrophobic compounds, less polar. Electrospray tends to favor more polar, non-volatile compounds. APCI gets down a little bit further into GC territory, and atmospheric pressure photoionization goes even further into GC territory, where you can analyze really hydrophobic compounds by Lcms. So. The other thing I'm going to focus on, we're going to sort of, I talked on Monday about the different experiments you can do, just a full scan MS mode, selected ion monitoring where you're just monitoring one ion. And I also talked about multiple reaction monitoring, where you're taking advantage of a dual mass analyzer mass spec to get 2 dimensions of selectivity, 2 dimensions of separation based on the unique mass of components of the analyte you're interested in. So the examples I'll give, we're going to talk about Lcms-MS. And the power of MS-MS is that we can set up the mass specs so that you're detecting specifically compounds with a specific molecular mass that fragment to fragment ions or product ions that have a specific molecular mass specific to that parent. So the selectivity of that experiment becomes very high, and the sensitivity increases when we do an experiment. So if we're going to do an MRM, we want to identify both the mass to charge ratio of the parent compound that we're interested in, and we want to identify a specific mass to charge ratio of some ion, some fragment ion that's specific to that parent, so that we can do this sort of 2-dimensional mass-based separation. So what we do is do a daughter scan up front. What we're going to do, if we're going to do quantitation, we probably have commercially available standards or synthetic standards for what we're going to do, or we aren't going to be able to make a standard curve. So we take that standard and we just infuse it with a syringe pump into the mass spec. And we monitor, we do a full scan mass spec to get the M/Z value of the parent that's expected. Once we're observing that and we've tuned the mass spec to maximize the intensity of that parent ion to maximize our sensitivity, we can now do a daughter scan to identify specific fragments that are unique to that parent compound or that precursor compound. That's called a daughter scan. So what we're going to do is form our ions in the ionization source by electrospray. We're going to filter through the parent ion or precursor ion of specific mass to charge. This is a daughter ion scan of epigallocatechin gallate, which is a polyphenol that's found in chocolate and tea. It's got some health beneficial antioxidant nutrition industry. So we're going to set up that first quadrupole to filter through M over Z 459, which is the compound we're interested in quantifying. Let that go into the collision cell, introduce argon into the collision cell, and break that M over Z 459 ion into pieces. And then we're going to scan the second mass analyzer, or the third quadrupole, and get a full mass spectrum that results from fragmenting that parent ions. And because we're only filtering through that single ion here, we know all of the peaks we see in the daughter ion scan are going to be specific to that compound. When you do that and get a full mass spectrum, you get a mass spectrum such as that shown here. Here's our precursor ion 459 that we filtered through the first quadrupole, broke it into pieces. You lose gallic acid from the 459, you get a 307. You lose another water or hydroxyl off of that, minus 18 Daltons, and you get your 289. And then the ion actually goes through, I won't show it, but it's a retro-Diels-Alder gas phase chemistry that breaks down, and you get this very characteristic ion of polyphenols and catechins at 139. So now what we can do, now that we have this sort of list of daughter ions that are specific to that parent, we can set up a multiple reaction monitoring experiment. And what we're going to do here in an MRM experiment is we're going to make use of the information we got in the daughter ion scan to get 2 dimensions of selectivity with our NSMS instrumentation. We're going to use both quadrupoles as an ion filter to only detect one compound in a complex mixture. So we'll form our ions. In the case of the 459, before we would filter through 459, break it into pieces, and then we might set this up to filter only through that big 139 peak, or the 307, or the 289, whatever we saw in that previous scan. And you want to set up, when you're doing quantitation, you want to set up for every compound at least 2 transitions for that compound for verification of identity. You don't want to just, for instance, look at the parent compound and then loss of water, because lots of things can lose water. So to maximize the selectivity and to maximize your confidence that you're identifying the right compound, it's always a good idea to set up at least 2 MRM transitions per compound. The more the better. But you don't want to end up with an MRM method where you're monitoring a suite of compounds and you have 300 MRM transitions, because you'll take a hit in sensitivity. So there's a balance there. But this is just an illustration of a different suite of compounds where we've set up an MRM transition. These are all glycolytic intermediates from glycolysis, central metabolism of eukaryotes and prokaryotes. So we've got fructose 1,6-bisphosphate, glucose, 2,3-phosphoglycerate, et cetera, et cetera. So we can take a cell extract from a bacterium and set up a method with MRM transitions, parent to fragment transitions for all of these different compounds, and monitor those simultaneously in one experiment. And every time you see that MRM transition within the mass spec, you're going to get a chromatograph. And then go in and measure the areas of those with standards, form a calibration curve, and do your quantitation. Any questions on that? Kind of how you think about setting up a LCMS-MS experiment for at least the mass spec portion of an LCMS-MS experiment. You can be lazy. You can be a lazy chromatographer in a lot of cases, and because we have 2 dimensions of mass separation using the mass spec, not require perfect chromatographic separation of these analytes, which we certainly do not have in this case. But even though they're co-eluting, you've got 2 dimensions of mass selectivity, so that you still get a peak that's very specific to the compound of interest. The caveat there is that you may get some analyte suppression, which we'll talk about in a minute. You have co-eluting compounds. There's only so much charge to go around in an electrospray ionization source. So if one is kind of stealing the fire of the other, you might suppress that signal, and your sensitivity may decrease for a specific compound. In which case, you're going to want to go and optimize your chromatography to get those things separated. There are also other interferences that can take place. Or you may have structural isomers that have identical mass spectral behavior and fragment identically, but you have to separate them chromatographically in order to quantify the individual compounds or the individual isomers of a particular class of compounds. Ready to move on? So let's talk about an example, and the first example I'm going to give is external calibration quantitation, and we'll pick a drug of abuse in urine as a very simple example of something one might do in a forensics lab as an example of how to do quantitation. So morphine has a nominal molecular mass of 285. When you protonate it, you get an M plus H plus ion of 286. If you go in and infuse morphine into your mass spec and break it into pieces, one of the fragments you'll see is a fragment of mass to charge 165. So we can set up an MRM transition on a triple quadrupole mass spec where we use the first quadrupole to filter through 286. Use the second quadrupole as a collision cell, break it into pieces. Use the third quadrupole as a mass filter to only filter through 165. And we'll only see morphine when it elutes right there. This is an MRM method where we have different transitions for 1, 2, 3, 4, 5, 6, 7, 8 different drugs of abuse, so you can run a whole panel. Each one of those peaks on there will have a different MRM transition that's being monitored. That 286 to 165, when you monitor that, the only peak you'll see is that one right down there for morphine. This is showing all the transitions simultaneously in different curves. So now we've got a method to separate this out in urine, and we can detect it by monitoring 286 to 165. So your basic quantitation protocol, if you were to do this by external standard calibration, just running standards, would be to set up a number of standards of your morphine. Now, what do you think we should make our standards in before we run them? If our ultimate goal is taking urine samples, monitoring morphine in urine, what should we make up our standards in? Should we make them up in water? Or should we make them up?
Ideally, we could use urine, but
yeah. What do we want to make sure of in the urine that we use? So we go and get an Erlenmeyer flask full or a vial full that we're going to use for our standard matrix. Is there any experiment you want to run beforehand before we make up the standards in that urine?
Make sure it's blank.
Yeah, exactly. So if we happen to get a urine sample of somebody who had morphine in the urine and we've got a big peak, now the concentration is going to be higher than we think it is when we make up our standards. So after we talk about this, we'll talk specifically why it's a good idea to use a matrix for your standards that's similar to the matrix you're doing quantitation. Sometimes it can't be done, and if it can't be done, there's things we can do. And we'll talk about that too. If you're doing external calibration, it's an absolute must without an internal standard present that you make up your standards in the same matrix you're quantifying. So for simplicity, we'll set up, 6, we'll have a blank urine, which we've just verified is blank. And then we'll have increasing, 0.01 micrograms per mil morphine, 0.1, 1, 10, 100. And we're going to run each of those on our Lcms MS method. Monitor our 286 to 165 transition, or whichever other transitions for morphine you want to monitor. And then you're going to make a simple calibration of morphine in micrograms per mil versus MS response. If your blank is blank, it'll be right down here, and hopefully going up by an order of magnitude in each of our standards, you get a nice linear calibration curve, we perform a linear regression on it, and you get the equation of the line. You can then go in, take your unknowns, so you've got a suite of samples from patients or people that you want to monitor this in. You run your method, you measure the area under the curve for morphine, which is this response. You bring that over, come down here and use the equation of the line to get the concentration of morphine in the urine. Now there's other types of quantitation you might want to do that aren't concentration of something in some fluid. EGCG that we talked about, and I showed the MS-MS transition for it. It's present in chocolate. It's present in tea. So you may want to monitor the concentration of something in a solid. It's a little more challenging. What you're going to want to do then is you're quantifying sort of mass ratio, the mass of EGCG per mass of chocolate. And in that case, some greater care needs to be taken up front from the standpoint of sample prep. But your basic game, you're going to do some sort of extraction of the chocolate and then compare it to standards and do your quantitation. What do you think are some of the limitations and pitfalls of doing what we just did? Taking standards, putting them in urine, making a standard curve, and then running urine samples and using that to quantify. Or alternatively, what might be some of the limitations if you're quantifying something, say, in chocolate, and you've got 5 chocolate samples and you want to quantify EGCG in chocolate, and you have to do an extraction up front on the chocolate, so you measure out carefully 5 milligrams of chocolate for 5 different samples, and then you do a hexane extraction to get rid of the fat, and then you do methanol extractions to pull out the EGCG, and then you're going to take it to the instrument and inject it and monitor the area. Any thoughts? What?
You lose the sample?
Yeah, sample losses. Bad hands in the laboratory. Especially where you're talking about doing extractions and sample, pre-purification from solids. If you're talking about concentration in urine and you have 2 millurine sample and you spill a little on the floor, that concentration is going to be the same in what's left. But if you've carefully measured out, milligram quantities of a solid, and then you're doing and then you do your first hexane extraction, you get a liquid, and one of them falls over and tips over in the lab. Now, we don't have the same mass of the compound you're quantifying in the tube as we used to have. So you can get sample preparation losses just right at the bench. Any others? I saw a hand go up. Yeah.
Well, you might not always be able to make up your standards in the same, like a similar matrix. That could be a limitation.
Yep. So if you, and we'll talk about a specific problem of that, and that is, depending on what matrix you're running in, it's going to affect the response of your compound. So this kind of goes hand in hand with what we were talking about before with sample losses. You can also get losses if you're doing some sort of sample pretreatment. When you're dealing with really complex mixtures, a chunk of chocolate or another piece of food or river water, if you can't just dilute, shoot, and get a nice signal for your compound, that complex mixture, no matter how powerful Lcms MS is in terms of sensitivity and detecting things in complex mixtures, sometimes you just don't get a good response because the matrix is an absolute mess, in which case you're forced to do some sort of sample pretreatment. Very often what people will do is solid phase extraction. So they'll add their matrix to a tube with a bed of C18 reverse phase chromatography reagent on it, wash it, load it, wash off all the polar junk and everything, and then elute off your compounds of interest, and then go to the mass spec LCMS instrument and do your quantitation. So if you don't get 100% yield here, which you never do, and you haven't added some internal standard to compensate for losses and for lack of yield on your sample pretreatment device, all bets are off for accurate quantitation. Analyte instability. If you've got a compound and you make it up and you do an extraction and you've got your samples here, but over time in the autosampler for the LCMS, MS, or while these things are waiting to be analyzed in triplicate on the MS instrument, the analyte is starting to break down or hydrolyze. You're going to get an artificially low concentration for it because it's broken down. Source contamination. Again, you've got 48 samples to run. You're going to run them all in triplicate. And here's an extreme example of someone running some samples with a phosphate buffer, where over time, as you start to run these replicate injections in a complex mixture, your source starts to get filthy, and that decreases the sensitivity, it decreases the response of your compounds. Now the sample that you ran as your 102nd sample versus the sample you ran as your 12th sample has a far lower response, and is going to give you an artificially low concentration. Finally, matrix suppression, and this is to your point of using a matrix. Unless you have a matrix that's absolutely identical for your standards as it is for your samples, you get what's called matrix suppression. So as I said before, within the mass spec ionization source, there's only so much charge that can go around to the analytes so that they can be charged, go into the gas phase, and be detected. When you put that into a sample matrix and there's all of these sort of impurities and contaminants co-eluting with your analytes of interest, what that does is artificially suppress the signal. So this is a good example of that. What these investigators did was just take an HPLC pump, and they did they had a flow rate of 0.25 mils per minute into the electrospray, and they did a constant syringe pump injection post-column into the electrospray mass spec of phenacetin, and then monitored that MRM transition specific for phenacetin. So if it's just being infused with HPLC mobile phase, you have this nice constant total ion due to the phenacetin signal. And then you do an injection of mobile phase onto the LC pump, and it has no effect on the overall signal of phenacetin. But if you monitor this phenacetin signal and then do an injection of plasma, a very complex mixture, boom, you've got about a 50% reduction in the overall signal for phenacetin. So if you happen to be analyzing your analyte of interest in a mixture that's more complex or has more impurities or contaminants or happens to have something co-eluting with your compound of interest versus what was happening in the standards, you're going to get this artificial suppression of the signal and get an artificially low concentration calculated. So I've mentioned this a couple times in quick passing. We'll see if you were listening. But what do we do to overcome these limitations? Yep, internal standard. So just to review, limitations of external standard quantitation, you're not going to have any compensation for sample handling losses, analyte instability, matrix interference or suppression, and signal degradation over time due to MS source contamination. Those are your four primary problems with doing external standard quantitation by mass spec. And the gold standard, internal standard for doing MS/MS is getting the identical compound that you're quantifying that's isotopically labeled stable. So either deuterated or N15 or C13 labeled version of the compound you're interested in quantifying, because it's going to chromatograph identically, its mass spec behavior is going to be identical. The only difference is there's going to be a mass shift. So they're going to co-elute through all of your sample prep, through all of your wet chemistry, through all of your, everything you do prior to analysis of this using the mass spec, it's going to behave identically to the analyte of interest. So if there's matrix suppression, there's going to be equal suppression of your deuterated internal standard as there is of your unlabeled standard, so that the ratio of those two will remain unchanged. So we're going to do the same exact experiment here, and it's going to, except we're going to do isotope dilution LCMS-MS. And what isotope dilution LCMS-MS means is that you're diluting your standards and samples in an isotopically labeled internal standard that's going to compensate for sample handling losses, matrix suppression, et cetera, et cetera. So everything's going to be the same here in how we approach this, except we're going to add an MRM transition. So if we have triply deuterated morphine as our internal standard, we're going to set up our mass spec method to not only monitor 286 to 165, but 289 to 168. And then instead of just monitoring the area under the peak of 286 to 165, we're going to measure the area of the peak underneath 286 to 165, and we're going to ratio it to the area of the peak under 289 to 168. So this, our x-axis in our standard curve, is going to become a response ratio rather than a concentration. And this is going to be morphine over D3 morphine. And our x-axis, rather than concentration of morphine, is going to become a mass ratio of morphine to D3 morphine. So because we're measuring the ratio of the unlabeled to the labeled analyte, the standard curve is going to look very similar. But let's say we have matrix suppression, okay? It suppresses the analyte signal co-eluting with the morphine. It's going to suppress both of these to the same extent because they're going to be identical. So the ratio remains the same. This ratio measurement remains unchanged. And the mass ratio that you have in your standard remains unchanged. It remains unchanged even if you spill half of it on the floor. If you add your internal standard and then you do solid phase extraction and you get a 72% yield on your solid phase extraction, you've lost just as much deuterated internal standard as you have the unlabeled analyte. So the ratio remains constant regardless of the yield of your sample preparation. Does that make sense? So then we get this. We're measuring response ratio versus mass ratio. Now, in our samples, we're taking the raw sample, we're spiking in a known amount, precisely known amount of internal standard to every one of our samples. So we know the mass of D3 morphine. We can measure the response ratio in the samples here. Come over here, use the equation of the line to calculate the mass ratio, and knowing the mass of D3 morphine in the sample that you've spiked in, you can calculate the mass of morphine in your sample. We'll do that. So regardless of whether you're doing solids, liquids, what your sample matrix is, by spiking that into that precisely known amount of internal standard into your sample prior to doing sample handling, extraction, bringing it over to the LCMS, letting it sit there for 3 hours waiting to be analyzed, mass spec source starts to get dirty, the overall responses come down, but those ratios remain unchanged so that you still get accurate quantitation. Compensating for sample handling losses, analyte instability. You're compensating for losses during extraction and pre-purification of analytes, and you're compensating for fluctuations in NS performance. And you'll see, even without the mass spec source getting dirty, Electrospray Ionization isn't, it's stable, but it's not incredibly stable. You can do 3 replicate injections and look at the overall peak area, and you get some jumping around. So you're going to sacrifice accuracy just due to sample-to-sample ionization. That will be compensated for by addition. Matrix interference, matrix suppression, source contamination. Like I said before, mass spec, doesn't eliminate the need for chromatography. When you've got really bad coelution, I mean, morphine's coming out in a chromatogram right here. You're monitoring your MRM for morphine. You look at the total ion chromatogram in a full scan experiment, and you've got this big blob of junk from your matrix coming out underneath this. Very often when you do your first sort of proof of principle experiments, looking, I'm going to quantify this compound in this matrix, what you'll find is that your sensitivity is terrible, even with mass spec. And the reason then you go and do your full scan experiment and you see that there's this huge protein or huge blob of stuff coming out, and it's suppressing the signal so severely that you're not going to be able to do quantitation even with an internal standard. In which case, you've got to use the power of chromatography to change your chromatographic conditions, column, mobile phase, to get what you want away from all of the junk. And then boom, your signal comes up through the lack of matrix suppression, and you have a nice quantitative method. And the other thing that I mentioned before was, I mean, very often you'll be looking for compounds for which there's a diastereomer, for which there are structural isomers, and in which case chromatography is actually absolutely essential because you have to separate them chromatographically because their mass spectral behavior is the same. There are different levels of isotope dilution quantitation you can do in terms of how accurate you want to be. If you want to develop a standard reference material at NIST, you're going to be a lot more particular about how you do your internal standard quantitation than you are if you just want a quick and dirty idea of how much compound is in a sample. So the simplest thing to do and the simplest way to do isotope dilution, Lcms, MS, is you make up your set of standards. The other thing that I didn't mention about isotope dilution is you no longer have an absolute requirement. Although it helps, if you can do it, it's going to be superior. But you no longer have an absolute requirement to make up your standards in the same matrix that you're analyzing in. Because if I make up my standards in water, but that mass ratio and the response ratio remains constant. Even if I go to a sample now and it's in urine, the urine's going to suppress that signal, but the ratio is going to remain unchanged. So you no longer have the absolute requirement to make up your standards in the same matrix. So 2 typical simple isotope dilution quantitation experiments might be you have a set of standards, your set of standards in water, or you have your set of standards in a good blank matrix, preferably. But if the matrix you have, you cannot get a complete blank, you're going to have to do it in water, something as similar as possible to the matrix of interest. And then you've got your 50 samples. And you take your volume to all of your samples, and you add a 10th volume, or to all your standards, and you add a 10th volume to all of your samples. And then you run them all. That's going to give you pretty good quantitation, but you're at the mercy of the accuracy of the pipette. You're at the mercy of your skill in consistently pipetting 100 microliters of everything into all of your samples. So you'll get a little bit of fluctuation depending on how good you are with pipette, and hopefully nothing. If you want to do highly accurate mass spec, you want to measure these mass ratios very, very precisely, and you're going to do that by weight. So you're going to go into the weighing room with a high accuracy scale, and you're going to actually pipette for your standards. You're going to have, you know, a tube of very precisely known concentration of your analyte and your internal standard. And then you're going to put your vial on the scale, and you're going to pipette 100 microliters of your analyte into your standard matrix, and you're going to weigh it 5 decimal places, and then you're going to add your internal standard, and you're going to weigh it again, and you're going to keep track of all those masses to get a very accurate measure of mass ratio. And then you're going to add a very precisely known amount of your internal standard to your samples prior to doing any sample prep. So let's say you're doing quantitation of catechins in chocolate. And you need to do a hexane extraction followed by triplicate methanol extractions of the chocolate to get rid of the fat, to pull out the EGCG, to do all of that. You're going to take your samples of chocolate, you're going to take a solution of your internal standard that you took a solid, added it to the bottom of the tube, measured it to 1,000th of a milligram on a high accuracy scale. You're going to add in your solution to dissolve it in. You're going to weigh it again so that you know the exact mass that you're adding per unit volume in your internal standard and for your standard. You're going to take your samples of chocolate, you're going to pipette in that internal standard solution, and you're going to weigh how much you pipette it in. So you have a very precisely known mass of internal standard in your samples. And you're going to make up your sample, or your standards, like I just said. Measure very precisely the mass of analyte you add, the mass of internal standard you add, so that you know that mass ratio perfectly. And then go and analyze your samples. And by doing everything by weight, you're going to be much more accurate. It's amazing when you go into a weighing lab. I worked at NIST for 4 years. So when we did quantitation, it had to be very, very, very accurate. And we have, you know, $45,000 scales in their weighing room. And you go in there, and it's unbelievable how pipetting 100 microliters, pop, 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 and weighing each one of those, how different they are. Pipettes are not very precise. And the volume they give in terms of doing highly accurate quantitation, good for everyday lab applications. So depending on how perfect you want to quantify, you may do quantitation in one of 2 ways. You do it via concentration, or you do it by mass. Doing it by mass is much more accurate. Any questions? That's about all I have in terms of material. I'm happy to talk about any specific applications you want to talk about. Yeah.
Using calibration, what do you do in limit detection and quantitation?
Oh, good question. Different people do it different ways. Typically, limit of quantitation is determined by 3 times the signal to noise. Limit of quantitation is sort of the concentration at which you can, in a statistically consistent way, get a 3-to-1 signal to noise ratio for that standard or whatever matrix. So you can go in, look at your peak areas, measure your noise level, measure your signal ratio, and do that several times to make it statistically relevant. And typically people define that as 3-to-1. And then we'll define limit of quantitation as that concentration at which you have consistently 10-to-1 signal to noise ratio. So you can either make serial dilutions to get to that point where you're measuring approximately 3-to-1 or approximately 10-to-1. Or at your LOQ and LOD, or you can do some extrapolation. So you run a 5 ppm standard. And it's 50 to 1, then your LQ with quantitation is probably 1 ppm, or you're going to get presumably a 10 signal to noise ratio. You can be more or less statistically rigorous in defining those, but typically 3 to 1 signal to noise ratio is defined as your LOD, and 10 to 1 as your LOQ. The other thing you want when you add your internal standard when you're doing quantitation is to add it at a level so that its response is similar to the response of your analyte in whatever samples you're analyzing. If you add internal standard and it's 1,000-fold more concentrated than your analyte of interest, you're going to get suppression, severe suppression by your internal standard. Things are going to get ugly. So you want that to be, optimally, you're adding internal standard where you're, at about that midway point on your standard curve. Anything else? Anything from the previous lecture that was unclear that you want to talk about? All right, you guys can leave a full minute. Thanks for your attention.